Hello, today is a very special day to me, Pie Day. No, not the baked dish, which is usually made of pastry dough casing that contains a filling of various sweet or savory ingredients. No, I am talking about the beloved mathematical constant, pi, which is approximately 3.14159 and its digits have no end. People have calculated and memorized a very large amount of the digits. The number of digits that have been computed is 50 trillion, and the world record for digits memorized is 100,000, which is only slightly more impressive than how many digits I have memorized of 1/3. But anyway, that's not what you're here for. You are here for the two alternative proofs that the volume of a sphere is 4/3 pi r cubed. So now on to proof number 1, the one that doesn't use calculus. It starts with 3 square-based pyramids and a cube, and you might notice that all 3 pyramids fit inside the cube, which means that the volume of one of these pyramids is 1/3 the volume of the cube it fits inside. Wonderful. But these pyramids are kinda slanted, but have no fear, not so slanted pyramids are also 1/3 the cube that they sit in. Observe. These pyramids are just a bunch of infinitesimally small squares sitting on top of each other. Now say we slide all the infinitesimally small slices to the middle and check it out. It's the same volume, just unslanted. So the volume of any square-based pyramid is just the volume of the cube divided by 3. Now imagine we traded in our infinitely many squares for rectangles and change our cube out for a cuboid. Look, it's still 1/3 the volume of the cuboid. Now imagine these rectangles slowly morph into circles, and your cuboid slowly morphs into a cylinder. Our pyramid is now a cone, but it's still 1/3 the volume of a cylinder it sits inside. Now that is neat and all, but that doesn't say anything about the volume of a sphere. Yet. For that we must turn to Archimedes' proof. It starts with a cylinder and a sphere, which just barely fits inside the cylinder. Let's observe only the top half for now, and let's ask, what is the volume of the non-sphere part? It happens to look like a bunch of infinitesimally small disks sitting on top of each other with bigger and bigger gaps. And there are 3 numbers to consider here: x, the radius of the gap, h, the height from the center, and r, the radius. And x squared plus h squared is equal to r squared by Pythagoras' theorem. We want the area of the r radius disks minus the x radius disks, which with a little algebra is equal to the area of the h radius disk, which says that the volume of this portion of the cylinder can be written as the volume of a cone, which is equal to 1/3 the volume of the half cylinder we were talking about. And so the volume of the cylinder without the sphere is 2/3 pi r cubed, and the volume of the sphere without the cylinder is 4/3 pi r cubed, and that concludes Archimedes' proof. Now on to the second proof, the one that uses calculus. What we are going to do is construct a solid of revolution of the graph x squared plus y squared equals r squared from -r to r. Now to unpack what this is saying, basically what a solid of revolution is to take a graph and rotate it around the x-axis and find the volume of this new solid that you've created. Since a sphere is just a rotated semicircle, we can find the volume by saying that the sphere is just a bunch of infinitely small cylinders stacked on top of each other with a width dx and a radius of y. And so what we need to do is just add up all the volumes of these infinitely small cylinders together and we get the volume of a sphere. And this is where the calculus comes in. Whenever we need to add up infinitely many infinitesimally small things, we use an integral, and so it goes like this. We write down the volume of a cylinder, in this case pi times y squared times dx. And since y equals the square root of r squared minus x squared, we instead write down pi times r squared minus x squared times dx. And we integrate from -r to r, pi times r squared minus x squared times dx, since the semicircle starts at -r and ends at r. Now to calculate this integral, we can take out the pi and hopefully not forget it, and the r squared turns into r squared times x, and the -x squared turns to -x cubed over 3, and we plug in our r and subtract the -r, then remember the pi that we almost forgot, and we get 4/3 pi r cubed, and there you have it, 2 alternative proofs for the volume of a sphere. Have a happy Pi Day, and thanks for watching.